Well, my dear students, we are again back to the course e-content course on technology of metal forming. As you remember, the first lecture, that is the last one, we started with the technological aspect of metal forming, wherein we covered very basic things, means what is technology, what is metal forming, and how the course emerged into uh, technology of metal forming, and what are the forming processes, the type of loading, the stresses we come across, and then we also discuss that when you form, the yielding takes place, then the flow stress, then the role of in strain, and then the temperature, and all those things we discuss. So we would further continue the same lecture here, with the hope you might have gone through the first lecture. So as I said, the forming, any forming operation, the temperature is very important. Apart from that, the strain rate sensitivity, this, when you do it on cold forming, then there is strain hardening. So if you heat it up, maybe the warm working or hot working, then the load requirement is less and all that. But another very important aspect is the strain rate. So what happens to the strain rate? As you know, the average stress that we last time we could show you the formula, which is y bar f, which is capital C strain rate raised to the power m, where epsilon dot is the strain rate. So the strain rate is strongly affected by temperature, as I said earlier also, right. So the usual function becomes the average strain, the stress, as A epsilon raised to the power n, and it's my epsilon dot, that is the strain rate raised to the power m. A is a strength coefficient. So look at this figure. So to understand the effect of temperature at different temperature and different strain rate, say let us see what happens to the flow stress YF. Okay. So look at the room temperature, right, where the strain rate is not very high, it is equal to 1, it is almost constant room temperature. So you know the flow stress is at very high, flow stress is required at room temperature, that corresponds to the cold case. Now if you increase the temperature to 400, now you see the nature of the flow stress drops, and it is, and further if at corresponding different strain rate you have different values. So if you further drop the temperature, say at 800, you find a linear trend, and if you further drop to 1200 degrees centigrade, you see the flow stress at lower strain rate is considerably dropped, and at higher strain rate it goes increases. So what this plot signifies, that at higher temperature and at higher strain rate you have the slope of the flow stress increases, right. So the phenomenon at productivity, when it is concerned, we concerned with the strain rate, and when we come across the hot forming at high strain rate, so that's how we mix it, but the thing is that as I said in the beginning, you have to produce a defect free product. So for any forming processes, you are not very free to choose any high temperature, because a very high temperature may cause defect, may cause a different kind of problems. So one has to choose a proper strain rate and proper temperature, so that you get a proper good product without any defect. Usually any deformation is carried out in some time t, and this result in as a the average strain rate. So we say that if Wm is the in percentage the mean strain rate, and phi is the degree of deformation, and t is the deformation time t, then one can define the mean strain rate. So mean strain rate Wm can be written as phi by t, which is the degree of deformation divided by deformation time. Okay. So it may however also be determined by the ram or slide velocity and the initial height of the workpiece, like in case of forging, etc. So in that case, if we define the strain rate as the that is the degree of deformation uh, in terms of the strain rate per second, okay. So this can be defined as strain rate as V by H0, where V is in meter per second, that is the velocity of the ram or slide, and H0 is the height of the blank. So we can define in terms of the velocity. As far as the flow stress is concerned for different materials, including the soft materials, as you know, the flow stress, particularly in cold forming, one can see here in this slide, corresponds to in terms of the specific strain energy. So if it is the flow stress, the corresponding to the K strength is the function of Fp multiplied by A, which is again function of phi p multiplied by A in Newton mm per mm cube. That is the specific energy. So if you see this, for the different materials it has been plotted, the flow stress, that is the flow stress curve when you plot corresponding to two materials CK15 and soft annealed, if you see. So it has a different nature. So you see the value of A and corresponding to phi p value, which is in percentage. So that's a different nature. Okay. So the flow curve corresponds to the material type as well. So in metal forming, if one asks what is deformability, so the deformability means it's the ability of a material to be deformed, and basically it depends on the what is the chemical composition of the alloy or the material. So for an example, in steels, the cold deformability depends on the carbon content. The components of the alloy, like the nickel, chromium, vanadium, molybdenum or manganese part, and the phosphorus content. It has been observed that the higher the carbon content, and the phosphorus content and the alloy components, the lower is the deformability. Okay. So another the thing on which the deformability depends on the structure, the crystalline structure. That means the strain size, and above all the pyrolytic structure is very important. So the steel should be as fine grained as possible. Since the steel with the smaller or medium grain size, crystallines are easier to displace on the crystalline slip planes. Okay, so we require a finer one. The third one, the deformability depends on the heat treatment, as I said. And equally distributed structure is achieved by normalizing, that is above AC3 line, if you remember. And the also the fast cooling. So the resulting hardness is cancelled out by subsequent soft annealing, and which is around AC1 line, and only soft annealed material can be cold form. Okay, so that's the role of annealing, and that's how the formability can also be there. In fact, in some cases, if you look at the forming, when you come across the instability and all that, so the analysis is basically based not on the instantaneous flow stress, but it is done on the average value of the flow stress over the strain stress curve from the beginning of the strain to the final value that occurs during the deformation. So if you look at this figure where the stress strain curve indicating the location of average stress in region of the yield strength y, and the finish stress is shown here. So specific energy, and that's the stress k epsilon raised to the power n, that corresponds to the yield point, and then the that is the and then the upper yield point. So the mean flow stress, you know this equation, which is k epsilon f raised to power n 1 plus n, where you have epsilon f is the maximum strain value during deformation corresponding to. So the degree of deformation and the principal strain is very important in bulk forming process, whether it is a forging process, whether it is a rolling process, whether it is a extrusion process. The degree of deformability is very important. So when we come across the degree of deformation, it's a measure of the extent of a deformation, that is the degree. The calculation is generally made from the relation between an indefinitely small measurement difference, that is within dx, if you see the slab method, if you recall, and then existing measurements corresponding to x. So by integrating it into limits, that is x0 to x1, this can be reduced to this form where you have dx by x, and that's the natural log x1 by x0. When it is presumed that the volume of the body to be deformed remains constant during forming, so that is how we come across capital V, that is L0 W0 H0, and that is equal to L1 W and H1. So we call it as the volume constancy equation, and therefore the value will change according to the volume constancy equation. For an example, if you take this cuboid, so before forming with the measurements W0 L0, and after forming it becomes H1 W1 and H1. So how the things are going to change during the deformation, and that's how here there is a role, and we define three different terms like the degree of offsetting, the degree of lateral flow, and degree of elongation. So we may define it as a phi 1, phi 2 and phi 3. So degree of offsetting is that is the height, so natural log of h1 by h0. Then the lateral that is the W1 by W0 natural log, and the elongation is the natural log of L1 by L0. So, if the change of cross section or the change of the wall thickness are dominant values, so phi can also be determined from these values. Okay. So, for an example, in case of change in the wall thickness, so one can define natural log by S1 by S0. So, in case of change of the cross section, one can define also natural log of A1 by A0. So, likewise one can define. So, when we come across the as a whole volume, the sum of the three deformation in the three main directions, that is length, width and height, is equal to 0. That is the thing. So, that is loss in the height is gained in the width and length. So, that is how phi 1 plus phi 2 plus phi 3 has to be 0 summation. This means one of these three deformation is equal to the negative sum of the other two forms. So, and this the greatest deformation is known as the principal strain, therefore. So, phi p, and that is how it was shown as phi p, the greatest deformation. Okay. So, the greatest deformation is a characteristics the manufacturing process and enters into the calculation of the force and work. It is how the extent of the deformation is measured, right. So, the degree of deformation, that is material can withstand, how great is the deformability is can be taken from the table of standard values. In fact, it is shown, and that shows the permissible deformation. Okay. And even the workpiece can also be produced in a single pass, you know, if the actual deformation during its production is equal to or less than phi p max. Otherwise, several passes are required with intermediate annealing. So, that we will come in the say the multi-pass rolling, multi-pass wire drying and operations. So, that is how we concern with the total maximum deformation. Another very important issue in metal forming is the metallurgical aspects. So, when we form, the first thing is that we require that there is no defect at all, and then second thing we require that you achieve a good strength, and another thing very important is also the metallurgy. So, as you know, the metallurgy deals with material science that studies the physical and chemical behavior of metallic elements, their intermetallic compounds and their mixtures, that is called as the alloys. So, generally the common engineering materials, you know, the aluminum, chromium, copper, iron, magnesium, nickel, titanium and zinc are the common one. The most alloy are non-carbon alloy system, as steels and cast iron include ductile iron. Stainless steel or galvanized steels are also another form of the iron. Aluminium alloys and magnesium alloys are used for applications where strength and lightness are required. The copper nickel alloys such as Monal, nickel based super alloys like Inconel are used in high temperature applications such as turbochargers, pressure vessels and heat exchanger for extremely high temperature applications. So, here all these cases the metallurgy is also very important. So, in manufacturing, when we concern the metal forming processes, manufacturing by metal forming, so metallurgy is concerned with the production of metallic components for use in consumer or engineered products, and this involves the production of alloys, the shaping, the heat treatment and the surface treatment of the products. The task of the metallurgist is to achieve a balance between the material properties such as cost, weight, strength, toughness, hardness, corrosion, fatigue resistance and performance in temperature extremes, very high temperatures. And therefore we come across various kind of surface treatment as well. So if the blank, that is the sections or the wire or rods etc. as a blank, we are simply interested into molding die and then pressed, the die would be made unless after only a few units. So galling would occur, you know, in the die because of the cold welding between the workpiece and the die, and as a result burns would form on the die which would make the pressed part unusable. So for this reason the blank must be carefully prepared before pressing. So this preparation summed up as a surface treatment, and it includes pickling, phosphating, lubricating etc. So we very often we come across these treatments, surface treatment also, and it is also a part of strength and the metallurgy. Okay. So when we deal with the forming, we deal these also. Apart from that, as I mentioned, the main reason is that there is no defect apart from the high productivity and the requirement of the strength and metallurgical aspect. So we are hang up and one has to keep compromise between these all factors. So to choose a quick processing ways so that the defect does not appear, and we also come within the domain of the proper strength and all that, we usually come across the forming limit diagrams or curves. We always do it for most of the metal forming processes to see what are the safe region where one can work and what are the unsafe region where one has to avoid, because it will result into defects. So a forming limit diagram or curve is in fact basically used in sheet forming, in metal forming, for predicting forming behavior of a sheet metal. The diagram in fact attempts to provide a graphical description of the material failure tests such as the punch dome test etc. In order to determine whether a given region has failed, a mechanical test is performed. The mechanical test is performed by placing a circular mask on the workpiece prior to the deformation, and then the measuring the post deformation ellipse that is generated from the action on this circle, and by repeating the mechanical test to generate a range of stress state, the formability limit diagrams can be generated as a line at which failure is onset, and this provides a good guideline. So forming limit diagram is very popular not only in sheet forming, it becomes also popular for other forming processes, and we would be covering details in the subsequent lectures. So keeping these things in mind briefly, so what is technology of metal forming and associated issues we discussed so far, so that one can understand what actually we are going to see. So as far as the course content is concerned, particularly for the technology of metal forming, this part we would cover into two basic part A and part B. So the part A will cover the introduction to the technology of metal forming, and part B will cover the other forming processes. Okay. So let us see what part A we are going to cover in this course. So part A, you know, we would cover the classification of metal forming, like the what is cold forming, warm forming, hot forming, the flow stress and coefficient of friction, work of deformation, all that we have little bit touched here. And then the effect of temperature, strain rate, macrostructure, friction in metal working, tribology in metal forming, metal working lubricants, metallurgical aspects of metal forming, post forming heat treatments and defects in metal working, forming limit diagrams. Then we come to the different processes, like when we come to the forging. In case of forging, the introduction and the classification of forging, like the forging operations, the forging processes, and miscellaneous forging operations also we would discuss. The design of forging dies is very important, like the drop forging die design, upset forging die design. If time permit, we would cover all these. Then the forgeability. So the forgeability and then the forging temperature, the forging defects, forging equipments we would also cover. The strip forging, especially plane strain forging, upsetting under axial symmetry, all these things we are going to cover. The closed die forging with overlapping dies, closed die press forging with axial symmetry and overlapping dies, forces in impression die forging, we would cover in detail all these things. The second very important topic is rolling. So we would cover starting from the introduction to the classification of rolling process, like strip rolling and the work deformation and the roll separation forces and all these things, analysis of rolling process, limit of rolling, like dependent on the temperature variation and the forces on the rolls, forces on the, and then the 3 high mill, 4 high remill, simplified analysis and torque calculation and defects in rolling, we will consider all these things. The sheet metal forming is very interesting. So we would study the classification, the press tool operations, the shearing operations, the deep drying operations, spinning, bending, and miscellaneous other operations we would see. The sheet metal dies and defects in the sheet metal forming is also very important. We would discuss all these. As far as the wire drying and extrusion processes are concerned, we would discuss in detail, like under the zero friction case, the wire drying with friction, wire extrusion, and the with friction, hot extrusion, and all that we would consider. The strip drying with friction, strip extrusion with friction, reduction in strip drying, tube drying with stationary mandrel, all these things we would cover. The tube drying with moving mandrel, drying and extruding through stationary tools of circular. Practice in drying of metals, hydrostatic extrusion, practices in extrusion of metals, defects in drying and extrusion, drying and extrusion equipments and practices we would cover in detail this one. So this covers the part A. In the part B, like the tube sinking and ironing processes. So the what is tube sinking, the equilibrium equations and the rotatory symmetry, tube sinking with conical dies, tube sinking with other dies, nosing with a die of circular contour, tube ironing, and all that thing we will cover. And then the another class of forming that we call at unconventional forming processes. So we would discuss that also, and its classification. Then the high energy rate forming processes, high velocity rate forming processes, the gas mixture processes, and the criteria for formability would be discussed. So there are many other miscellaneous processes like the viscoplasticity, deformation theory of plasticity, thermoplasticity, theory of machining. We are not going to discuss much, but the microforming has become very new now, so we may touch a little bit on that. And some of the common materials that is used for forming of different through different processes like alloys, and we would superplasticity we would discuss. So these are the complete course content that we are going to cover under this course. As far as books are concerned, in fact there is no single book available so far that covers all the things, and that's how I have listed some of the books here, popular books here. You can refer it here, like the number one, the metal forming, which is the limit analysis by B. Avitzer. So the plasticity theory by Mendelssohn, engineering plasticity by Cadline, and very popular book, the introduction to engineering plasticity for G.K. Lal by G.K. Lal and Reddy. It's a good book, but it is more on the analysis side. As far as the technology side is concerned, you have Harris book number 6, then you have Dieter book that is on analysis side. The 8 is the G.W. Rowe, the principles of industrial metalworking processes by G.W. It's a very good book. Then the metal forming mechanics and metallurgy by Cadell, the fundamentals of metal forming processes by Juneja, and Chinet. Then the engineering plasticity by W. Johnson and Miller, and the Indian version of the other books, which is the technology of metal forming processes by Surinder Kumar, and metal forming process, which is published by HMT, is also very popular. Apart from that, there are many other books that one can follow. I have not listed much of them, but time to time there are good books on the technology side. So once these lectures chapter wise taken, I will give some of the books especially for those chapters. Okay, so this is what is the whole course content, and the way we are going to start with, we would start with forging, and then one by one we would cover. Hopefully the question answers are also a part, but it is left for you. You people can have question answer and tutorial part, so I am not going to cover those things here. So hopefully we would continue from the forging lectures next time. So thank you all very much for keeping patient, but please communicate your feedback to us so that we can improve. Okay, so thank you very much.